It hums silently beneath the surface of our world. It is an invisible giant. A force that powers our cities. It lights our homes. It drives our economies. This is the secret engine of civilization. An engine that runs on the heart of the atom. For decades, its true nature has been shrouded in fear and misunderstanding. But its story is not one of disaster. It is a story of human ingenuity. A story of staggering engineering. It is the blueprint for harnessing the most powerful force in the universe. This is how nuclear power really works. Act 1, the atomic dawn. Our story begins not in a power plant, but in a laboratory. The year is 1938. In Berlin, chemists Otto Hahn and Fritz Strassmann conduct a strange experiment. They bombard uranium with tiny particles called neutrons. They expect to find heavier elements. Instead, they find barium. An element roughly half the size of uranium. They are baffled. They write to their colleague, Lisa Meitner, an Austrian physicist who had fled to Sweden. Meitner and her nephew, Otto Frisch, contemplate the results. They walk through a snowy Swedish landscape. A revolutionary idea strikes them. The uranium nucleus wasn't chipping. It was splitting. It was breaking apart with unimaginable force. Frisch coined a term from cell biology. He called the process fission. In a single instant, the physics of our world had changed. The energy locked inside a single atom was immense. E equals mc squared. Einstein's famous equation was no longer theoretical. It was a terrifying, tangible reality. The world was on the brink of war. This discovery was immediately weaponized. The Manhattan Project was born. A secret city of scientists gathered in the New Mexico desert. Their goal was to build an atomic bomb. But a parallel path was also being forged. A path toward control, not destruction. In Chicago, a team was led by Italian physicist Enrico Fermi. Their goal was simpler, yet just as profound. They wanted to create the first self-sustaining nuclear chain reaction. Under the bleachers of a squash court at the University of Chicago. They built a crude machine. They had no advanced computers. They used slide rules and intuition. They stacked 45,000 graphite blocks. Graphite slows down neutrons, making fission more likely. They embedded slugs of uranium oxide and pure uranium metal. They called it Chicago Pile 1. It was, literally, a pile of materials. For safety, they had a man with an axe. He was ready to cut a rope holding a control rod. Another man stood ready to douse the pile in a cadmium solution. This was the raw, brutal frontier of science. On December 2, 1942, they began the experiment. Fermi ordered the cadmium-plated control rods withdrawn. They were pulled out by hand, inch by inch. Geiger counters clicked. The sound grew faster and faster. For 28 minutes, humanity's first artificial nuclear fire burned. It produced just half a watt of energy. Enough to power a tiny light bulb. But it was a monumental proof of concept. Humanity had tamed the atom. The war ended. The terrifying power of the bomb was revealed to the world. A new question emerged. Could this power be used for peace? In 1953, President Dwight D. Eisenhower delivered a famous speech. He called it Atoms for Peace. He envisioned a world where atomic energy powered cities. He promised electricity too cheap to meter. The dream was born. The secret engine would be brought out of the shadows. It would be transformed from a weapon of war into a tool of progress. The blueprint for a nuclear world was ready to be drawn. Act 2, the blueprint for a nuclear world. Building a nuclear power plant is a monumental task. It is one of the most complex machines ever created. The basic principle is surprisingly simple. It is a highly sophisticated way to boil water. The process begins in the reactor core. This is the heart of the plant. Inside the core are thousands of fuel rods. Long, thin tubes filled with pellets of uranium. But not just any uranium. Natural uranium is mostly U-238, which doesn't split easily. A tiny fraction, about 0.7%, is the isotope U-235. This is the fissile material. To create a sustained reaction, this concentration must be increased. This is the process of enrichment. It's a complex and energy-intensive industrial process. It separates U-235 from U-238. The enriched uranium pellets are sealed in the fuel rods. These rods are bundled together into fuel assemblies. The assemblies are then carefully lowered into the reactor core. The chain reaction begins. A stray neutron strikes a U-235 nucleus. The nucleus splits, releasing a massive amount of heat. It also releases 2 or 3 more neutrons. These new neutrons fly off and strike other U-235 atoms. This creates a chain reaction. Left unchecked, this reaction would grow exponentially in a fraction of a second. This is where the moderator comes in. The neutrons released by fission are too fast. They need to be slowed down to be effective. The moderator does this job. In most Western reactors, the moderator is simply water. The fuel rods are submerged in it. The neutrons collide with the hydrogen atoms in the water. They lose energy. They slow down. Now, they are ready to cause another fission event. To control the rate of the reaction, engineers use control rods. These are the brakes of the reactor. They are made of materials that absorb neutrons. Materials like boron or cadmium. To increase power, operators slowly withdraw the control rods. More neutrons are available for fission. To decrease power, they insert the rods. The rods soak up the neutrons, slowing the reaction down. In an emergency, the rods are slammed into the core in seconds. This is called a scram. The chain reaction stops almost instantly. The immense heat from fission must be captured. This is the job of the coolant. In a pressurized water reactor, or power, water is kept under extreme pressure. This prevents it from boiling, even at over 300 degrees Celsius. This superheated water is pumped through a steam generator. The heat is transferred to a separate loop of water. This second loop of water flashes into high-pressure steam. The steam is channeled through massive pipes. It strikes the blades of a giant turbine, spinning it at thousands of RPMs. The turbine spins a generator. And the generator produces electricity. This is the basic blueprint. Fission creates heat. Heat creates steam. Steam spins a turbine. This design choice became a strategic decision. The United States Navy had developed compact powers for its nuclear submarines. It was a proven, reliable technology. So America's commercial industry was built on the power. Other nations chose different paths. Canada developed the CANDU reactor. It uses natural, unenriched uranium. But it requires a more effective moderator, heavy water. The Soviet Union developed the RBMK. A large, graphite-moderated reactor. It was cheaper to build and could be refueled while operating. But it contained a dangerous design secret. The final layer of the blueprint is safety. The reactor is housed inside a massive containment building. A dome of steel reinforced concrete, several feet thick. It is designed to contain extreme pressures and temperatures. It is the last line of defense. A shield between the atomic heart and the outside world. Building these giants became a national mission. A symbol of technological prowess. They required billions of dollars. Decades of planning and construction. An army of engineers, welders, and physicists. The secret engine was being built, piece by piece, all across the globe. Act 3, Reinvention and the Future. The dream of cheap, limitless energy faced a harsh reality. The public grew wary. 3 major accidents would redefine the industry. They became brutal, but necessary, lessons in engineering. The first wake-up call was 3 Mile Island in 1979. A cooling circuit failed. A relief valve stuck open. But confusing instruments led operators to make critical errors. They misread the situation. They manually shut down the emergency cooling systems. The core overheated and partially melted. Crucially, the containment building worked. It held. Almost no radiation escaped. It was not a public health disaster. It was a human-machine interface disaster. The industry was forced to revolutionize its control rooms. It overhauled operator training and safety procedures. It was a painful, expensive lesson in human factors engineering. The second event was a true catastrophe. Chernobyl, 1986. The RBMK reactor had a fatal flaw. At low power, it had a positive void coefficient. If cooling water turned to steam, the reaction would speed up, not slow down. It was a runaway train with no brakes. During a reckless safety test, operators broke all the rules. They disabled safety systems. They put the reactor into this unstable, low-power state. A power surge began. They hit the scram button. But the control rods had a graphite tip. As they entered the core, they briefly displaced water. This momentarily increased the reaction rate. The result was a catastrophic steam explosion. It blew the 2,000-ton lid off the reactor. With no containment building, radioactive material was blasted into the atmosphere. Chernobyl was a failure of design and a complete collapse of safety culture. It taught the world a terrifying lesson. Safety cannot be an afterthought. It must be the first principle. And containment is non-negotiable. The third event was Fukushima Daiichi in 2011. The plant was hit by a magnitude 9.0 earthquake. The reactors performed perfectly. They scrammed as designed. But minutes later, a 15-meter tsunami struck. It was far larger than the plant's seawall was built for. The wave flooded the site. It knocked out the backup diesel generators. The systems designed to cool the reactor after shutdown had lost all power. The cores overheated. Hydrogen gas built up and exploded. The failure was not of the reactors themselves. It was a failure of imagination. A failure to plan for a disaster beyond the expected design basis. From these ashes, a new generation of reactors was born. Generation 3 plus designs like the AP1000. Their philosophy is different. They rely on passive safety. They use natural forces, not complex machinery. In the AP1000, a massive tank of water sits above the containment vessel. If all power is lost, a valve opens automatically. Gravity pulls the water down. It floods the outside of the reactor vessel, cooling the core without a single pump or operator action. It is engineering elegance. Simple, fundamental physics provides the ultimate failsafe. The innovation doesn't stop there. Scientists are now designing Generation 4 reactors. Molten salt reactors that can't melt down. Reactors that use nuclear waste as fuel. Small modular reactors, or SMRs, built in factories. They promise cheaper, faster deployment. And on the horizon, the ultimate prize. Nuclear fusion. The power source of the stars. In massive experiments like ITER in France, scientists are building magnetic bottles. Tokamaks that contain plasma heated to 150 million degrees Celsius. Fusing hydrogen atoms together to release clean, safe, and abundant energy. It is the hardest engineering challenge humanity has ever faced. But the promise is too great to ignore. The story of nuclear power is complex. It is a story of brilliance and hubris. Of dreams and of failures. But it is fundamentally a story of learning. Of relentlessly improving a technology with immense potential. The secret engine of civilization is still being perfected. And in a world desperate for clean, reliable energy, its hum may become the sound of our future.